Nanotechnology, organized by UGC-Malaviya Mission Teachers Training Center, University of Calcutta, which is the program is hosted at Maulana Azad College, Kolkata. And welcome to the lecture 15. For the lecture 15, our next resource person is Professor Krishna Poluri. Professor Poluri is currently working as a professor at Department of Biosciences and Bioengineering and Center for Nanotechnology at IIT Roorkee. Dr. Poluri completed his PhD from TIFR Mumbai and postdoctoral research from Rutgers University and University of Texas Medical Branch. His areas of expertise are biological, NMR, spectroscopy, technology, and algal biotechnology. He has published almost 200 publications, including research articles, editorials, books, and book chapters in various reputed international ACI journals, and filed 3 patents. He has received several national level awards, including H.S. Atre Award by NMRS in 2023, SARB Star Award in 2022, Innovative Young Biotechnologist Award in 2013 by DBT, Nasi Platinum Jubilee Young Scientist Award in 2013, and Young Scientist Award by Indian Science Congress Association in 2009. The, the title of his lecture is NMR Elucidation of Plastic Protein Surfaces for Functional Annotation. So I welcome Professor Poluri to start the session. Over to you, sir.
Yeah, thank you. Thank you very much for the invitation. I will just share my screen. So can you see my screen?
Yes, sir. It is visible.
Okay. So good morning to all. So today I have chosen a topic of explaining the importance of protein surfaces and everything for their functional annotation. Considering the fact that we are moving towards a era of biomolecular therapeutics rather than the small molecular therapeutics. People are looking for RNA-based drugs, DNA-based drugs, especially protein-based and peptide-based drugs. So my talk will be essentially in few parts, like sort of explaining you what is the basic of NMR spectroscopy, how it is useful. So a lot of people essentially in various fields related to the workshop also, like chemistry, nanotechnology and biotechnology, all of them use for a variety of applications. The other one is how we can use it for protein surfaces, and I will show you some of the examples, like how we can use engineering and how dynamic the proteins and so on and so forth. So please feel free to stop at any point, or we can discuss at the end of the thing. So I will show you a few examples of nano, also how we can use the NMR, and also in the protein context, since I am essentially in both the departments and working in both the areas. So you can have my email ID, and anything is needed, you please feel free to contact me at any point of time. Okay. So coming to the NMR spectroscopy, so this is one technique where multiple Nobel prizes have been given. So it started essentially, if you see, it started essentially with the physics, then went to the chemistry, and then biology. So initially for the development of magnetic moment and everything, then development of nuclear magnetic resonance spectroscopy. Then in 2002, it goes to the structural elucidation of biomolecules, especially proteins and everything, by NMR spectroscopy. And in 2003, essentially, it went to physiology and medicine for the discovery of magnetic resonance imaging technology, which now clinically all the major hospitals are having. So we have several of these techniques, which majority of them majorly we use nuclear magnetic resonance spectroscopy, magnetic resonance imaging, and also we use something called electron spin resonance spectroscopy. So these all essentially deal with either nuclear spin or with the electron spin. If we consider the biological material, it is like gas, liquid, solid, and so on and so forth. So we can do in principle the NMR spectroscopy for all of them. We don't do for gas, the reason being we may not get enough concentration of the spins which are present, but very often we do with liquid and solid. So in solids and liquids, you can take any liquid. People have done anything as long as you have a active spin, you can do it. I will show you what active spin is. So, and you will get atomic level information. As I showed you, you can do membranes, crystals, fibrils, glasses. You can always do paints, wood, whatever you want to do, you will do. So this is essentially how an NMR spectrometer look like. So it has essentially 3 or 4 parts. So one uh, so this is one. So you have 2, and this is 1, 3, and you have a workstation 4. So this is what you call it as a superconducting magnet. So where you maintain at 4 degree Kelvin, and here is the probe. You call it as a probe, which is essentially where you keep your sample. So you put the sample from top to bottom. So these are called auto samplers now, where you can use multiple samples. And this is the console where essentially you send radio frequency waves and also you collect the signals from it. And this is a workstation where you process the things. So this is what magnet. You have a probe, you have a console, and you have a computer, which is. So this is what you have a sample, which is the liquid state sample. Now this NMR spectrometer, if you see inside, so in one layer, the blue one, what you are seeing essentially will have liquid helium, and the brown one will have liquid nitrogen, so that the liquid helium won't be evaporated, and this probe is connected to your console preamplifiers, and then you will get a data out of it. So you have several of them, electronic circuits. So that is why NMR spectroscopy people are working, computational scientists are working, electronics people are working. So physicists are working, chemists are working, and so on and so forth. If you see the samples, you can have 2 different type of samples. One is solution state sample, and the other one is the solid state sample. In the solution state, essentially you put a liquid sample and you put it into the NMR spectrometer and you record it. So color or anything, it doesn't matter. The other one is solid state sample. You can take the solid and you can essentially load it into these rotors and you can record the spectra for the NMR. So that is how you can record both the liquid state and the solid state of a given sample. Now, as I told you, if you take the NMR spectroscopy, whatever any of the color which is present, okay, other than what you have is white background. So all these elements, you can do something called NMR spectroscopy. So that is why it is very popular. People have done NMR for lithium batteries. People have done for calcium signalings, calcium. So you can use TiO2 coatings, any of them, irrespective of, and people have identified nickel or any other heavy metal, so on and so forth. So lead, all these things you can essentially look for the NMR spectroscopy. So now this spectrum is dependent upon something called, as I told you, this is a spin spectroscopy. It is dependent upon spin quantum numbers. Essentially, the way why some element in a periodic table is active or not active is dependent on the number of protons and the number of neutrons present in a given system. So if they both are even, so then at the end you don't have a spin which is 0. If they are odd, you have integral. Integral means 1, 2, 3, 4, so on and so forth. If they are odd even or something, they are half integrals. That means half, 3 by 2, 5 by 2, so on and so forth. Now, even if something is even 0, suppose I will give you a simple example for you, like you take carbon. The carbon essentially is C612. So 6 plus 612, it is 0. But carbon, I put it as yellow. The reason being, if one of the carbon is 0, I can use something called C613, which is called the isotope. So that means NMR very cleverly uses these isotopes in such a way that one isotope is not useful, I can use the other isotope to identify and to get the signals. So that is how, when we have these atoms and all majority of the elements have isotopes, one way or the other you are going to get the information of this one. So now that is what you can see here, like you can use 19 of nitrogen instead of 14, you are using 15. Hydrogen you can use 1, heavy water, deuterium, and so on, so forth. The other factor which comes is essentially something called a gyromagnetic ratio. That means how strong, when you put this nuclei, it acts as a magnet. So the best is hydrogen, and rest of all of them are weaker than the hydrogen. That is why whenever you heard of something in your MSc or whenever in the PhD or something, NMR means essentially you call it as a proton NMR or hydrogen NMR. The reason being, of course, the protons are abundant, and the H1, the isotope abundance is also high, and also it gives very strong signals which are present. So of course, if you take a hydrogen and a carbon, the carbon is 1/4 of a hydrogen. So your signals will go much lower, and nitrogen is 1/10 of it. That is why people use all these elements here, but in general, due to the ease of doing experiments and the signal, always people prefer to have an doing an hydrogen based, or for all practical purposes in NMR, we call hydrogen as essentially a proton. Since it doesn't have a neutron, it's a proton. So when you record a spectrum of hydrogen for a ethanol, what you will see is, you see a different peak for C. The hydrogen of CH3 is different, the hydrogen of CH2 is different, the hydrogen of OH is different. The reason being, the chemical environments of all these are far different. That is why it is a atomic level technique. The reason being, whatever is the environment, according to the environment, the signals will do. Suppose if I take the hydrogen of oxygen, it is essentially added to an electronegative atom. So this, in this hydrogen, the electrons are pulled out. So this OH is connected to CH2, and CH3 is least affected by this electronegative oxygen. So as a result, so you have two ways of looking. One you call it as a upfield shift, and one you call it as a downfield shift. Upfield shift means you don't have influence of electronegative atoms or something. So it comes at upfield. When you have the electronegative atoms or hydrogen bonding or something, then it is come to downfield. So this you call it as, in terms of electrons which are present, this you call as shielding, and this you call it as de-shielding. So de-shielding means electrons are gone towards the electronegative atom. Shielding means the electrons are within place in well. So this tells, for a organic chemist or for a chemist, what people do is, essentially for every hydrogen, depending upon any sort of compound, we can tell where exactly the spectrum comes. You take a benzene, you take a uh, acetylene, or you take anything. So we can get this. That is what the chemists use. They know for each and every functional group and hydrogen where they can get this. So these people use as a database. If you see any of the chemist papers or something in the material methods, they give all something called the chemical shifts. So each and every proton where it appears, you call it as a chemical shift. This is essentially they provide to us. The same thing we can do for 13C also. So that means you can give the carbon also. So majority of the molecules are having hydrogen and carbon. So when we have hydrogen carbon, both of them, so it becomes much easier to identify the signals. As I told you, you have these three. What you end up is three different signals: CH3, CH2, OH. Okay, and if you see the signal length also, this is roughly 3 times, this is 2 times, and this is 1 time, which indicates there are 2 hydrogens here, there are 3 hydrogens here, and it's a 1 hydrogen. So the intensity represents essentially the integration, the number of hydrogens. So you can essentially calculate the number of hydrogens which are present on a given carbon also. But here if you take the OH and CH2, they are different. OH you call it as an exchangeable hydrogen. That means this hydrogen is always hopping with the solvent. Whereas CH2 and CH3, you call them as non-exchangeable hydrogens. You call it as non-exchangeable, and this is exchangeable. So now the spectra won't be as simple as this. Fortunately, the spectra looks like this. Okay, so this is a reference compound. What essentially the spectra looks is your CH3 will be coming as a triplet. Okay, so and your CH2 will come as a quartet, and your OH, as I said, it doesn't do anything. The reason being it is exchange. Now why you get a triplet or quartet is depending upon the number of hydrogens which are present in the next atom. So for CH3, the next one is CH2, so it splits into 2 plus 1, which is equal to 3 signals. And for CH2, the neighbor is 3 hydrogens, so it splits into 3 plus 1, which is 4. And they follow a pattern which you call it as a Pascal triangle. So they follow a pattern which you use called as a Pascal triangle. The intensity, suppose if there are 3 peaks, it is 1 is 2 is to 1, and if there are 3 peaks, it is 1 is 3 is 3 is 1. So this is called a Pascal triangle they follows. Now using this one and this, you call it as a coupling. Coupling means when 2 hydrogens are attached, they talk to each other, and that is why coupling is essentially interaction. Coupling means interaction. So in NMR, the interaction for any given molecule happens 2 types. One is called through bond coupling. You see this hydrogen and through this hydrogen. This is 1 bond, this is 2 bond, this is 3 bonds. So either through bonds it can happen, or if 1 hydrogen is here and 1 hydrogen is here, then interaction can happen through space. Okay, so that means it is as simple as you taking a telephone. You have either a cable, wire, or you have a wireless. The wireless is called the space, the cable is called the bond. So either you have through bond or you have through. So this will help you in identifying all the signals, and you can tell, you see, you can tell depending upon the interaction value. If they are close, they are high in interaction, then you can tell what sort of thing. That means if the interaction value is 6 to 9, you can tell it is orthoprotons, metaprotons, paraprotons, like that you can tell. So this 10 minutes I spent, the reason being these are the basics to understand any of these things. So I will show you a simple example. like sort of, if you take Cl, CH2, CH3, now you see the CH3 is divided into like 3. The reason being the next neighbor is 2, 2 plus 1, whereas this is divided. Now we measured a spectra and you get a doublet with J value of 2.3 H. So 2.3 H means these hydrogens are essentially present as meta hydrogens. So whether if you have a value, you can tell whether meta, or whether it is meta, you can also predict the values. So this is what something which we do, and now databases are there. Once you put your samples, you will get something. So the other one is, as I told you, one is if you have a hydrogen, you have another hydrogen. As I told you, one is through bonds. The other one is through space. Bonds are limited. When they are through bonds, you can only, it's your like mobile, it's your like telephone. You cannot carry all over the place in the house. You may have a wire which is like 1 feet, 2 feet, or 1 meter. So you have to talk in that area only. So that is why it is constrained. Similarly, the bond lengths are constrained. So 4 bonds means even if you take 1.5 Armstrong units per bond, you may go up to 6 Armstrong units or something, 5, 6 Armstrong units. So space, like sort of 4 bonds you can go space, here 1 and here 1, but these are not connected. These are connected through a very long polypeptide chain or protein chain. These two are not talking through bond. These two are talking through space. Okay, that you call it as nuclear Overhauser. Overhauser is essentially the scientist who discovered that these dipoles, okay, any of these fundamental particles can be considered as dipoles. So these dipoles talk through the space, which are like your point charges, q1, q2 by r square or something. Okay, so this is something. So that means if I have this proton and this proton, how do I know they are connected? If I perturb this one, if this fellow is perturbing, then they are connected through space. If they are not perturbing, then they are not connected through space. Before going to the examples, just another 2-3 minutes so that you have the little concept. One more thing we generally do is, if you remember, I told like hydrogen is very sensitive and carbon is very like 1/4 of sensitive and nitrogen is 1/10 of sensitive. So now if you take a hydrogen spectra, you will see a hydrogen spectra like this, very sensitive signal. If you do a carbon spectra, you get carbon like this. And it takes a lot of time to do with this NMR of carbon and everything. So now the question is, can I increase the signal of carbon? Okay, so that concept is essentially is a selective population transfer or polarization transfer. So what you do is you take a sensitive nucleus and you transfer the magnetization to a insensitive nucleus and you detect the insensitive nucleus. Since you are passing from a sensitive to the insensitive nucleus, it is essentially getting a better signal. This is like you have a person who is poor enough, you keep few months with a rich guy, irrespective of money is there or not there, the person starts behaving like a rich guy. So this is what you do, you transfer the magnetization to it. If you do this one, what happens is the signal intensities varies. So, and of course, this also follows a principle that the more the weaker, the better the gain it will be. So this is something what is used very commonly in NMR spectra. When you want to see, the idea is you cannot only run hydrogen, you have to run so many other nucleus. But how do you run if they are sensitive? If they are sensitive, the only way to run these are you pass this through. This is always the sensitive nucleus is hydrogen. The insensitive can be carbon, nitrogen, phosphorus, any of them. You do it. especially coming to the biological molecules, hydrogen, carbon, nitrogen, phosphorus, these are very important molecules to work with. Okay, so now that is the 15 minutes or something, whatever we have is essentially the basic things that terminology one has to remember. So now for the next whatever 45 minutes or 1 hour, I will show you more or less the examples, how to determine few examples of nanotechnology also, and few examples of how to determine protein structure and how you can use these protein structures, essentially different features for engineering of new proteins, or how protein dynamics and so on. So one of the example what I am showing here is the nanoparticle interaction. Suppose if you take a zinc oxide nanoparticles or something and you put in a uh, like dialysis bag or something. So the dialysis fluid will interact with these nanoparticles. Now the question is, with what component of dialysis fluid is like it is interacting? You have glucose, lactate, so on and so forth. What you can do is you can run these one-dimensional NMR spectroscopy. You can see here with glucose, even after increasing the concentration of nanoparticles, there is no much difference in the signal. But whereas when you increase the nanoparticle concentration, the lactate resonances are lost. So which indicates that the zinc oxide nanoparticles are essentially interacting with lactate but not with glucose. So you can do with so many citrate, lactate, and so on and so forth. You can also see, so from the black to the green, the signals are almost disappeared. Okay, so that indicates like how the nanoparticles aggregate or something, where it is interacting, we can have an idea. Similarly, what you can also do is, suppose you have the cadmium selenium quantum dots in different Wurtzite and other conformations. So whether you have the same crystallinity and conformation or not, you can see. So this is Wurtzite conformation. This is the another conformation. This is cadmium NMR spectroscopy. Similarly, you can do the cesium spectroscopy, whether cesium is in a bulk or cesium in a nanocomposite. So you can tell whether it is a bulk or nanocomposite. Similarly, this is cadmium nanoparticles, core shell nanoparticles. You can also tell cadmium is either present in the core or in the surface of the. So similarly, phosphorus is in the core or in the surface. So you have lot of information which is embedded in this, where you can talk about this one. So as the main topic today, we have chosen like that, we can tell where the link is, and so many, we can even evaluate the sizes of the nanoparticles, so on and so forth. You can do a lot of things using NMR spectroscopy for nano also. We do a lot of experiments for nanospectroscopy also. Now the other thing is, as I told you, today we are discussing about the protein and biomolecular spectroscopy. So let me go through it. So this is what the NMR spectroscopy, who has an idea of basic biochemistry and so on and so forth. So you take the protein remains as unfolded conformations, partially folded conformations, native conformations, and so on and so forth. Of course, they form oligomers, aggregates, so on and so forth. Now the thing is, you can identify all these conformations using NMR spectroscopy. You can even do the complex structures, and at the same time, you do something called NMR based metabolomics. You can essentially do the metabolomics of NMR. That means you can do a mixture of samples and everything. Okay, you can study the dynamics. NMR dynamics is very powerful. So from starting from picosecond time scale to the hours, you can do NMR dynamics, and at the same time, you can also study thermodynamics, kinetics, velocity. If you talk about structures, you can do a simple protein structure, you can do with a carbohydrate, you can do with DNA, RNA, or you can do a protein-protein interaction studies and everything. So lot much can be done, one can do in terms of proteins. So now when we look at for NMR spectroscopy or something, now the thing is, when you had ethanol or something, that is okay, you have three peaks. But when you take a protein or something, you will see the spectra like this. There are hundreds of things which are present, so which you will not able to say which peak belongs to which. That is why what you do is, when you take proteins, nucleic acids, so on and so forth, you have thousands of signals and you will not able to assign these signals. Now, how these thousands of signals to be assigned is something, what you do is, you increase the dimensionality of NMR. Simple. Dimensionality of NMR means, one dimension means I have a line here. Okay. Suppose I have 1000 points. Okay. I have 1000 points. I put 1000 points in the line. Of course, it is crowded. So now these 1000 points, I will put it in a square. Okay. This is called a two-dimensional NMR. So now I can visualize better. But these 1000 points, what if I put in a cube? Okay, I take a cube, I will put these 1000 points in a cube, and now every cube I will use as a slice. So I will cut this cube into different slices. So then every slice will have only 10 points, 15 points. So automatically I can identify, I can do the signals. So this is what you call it as something called a multi-dimensional NMR spectroscopy, or you go from one dimension to a two-dimension to a three-dimensional NMR spectroscopy. The other advantage is, if you take one dimension, you have always hydrogen. If you take two dimension, you have hydrogen on one dimension. Since I said always you need to have one sensitive nucleus, the other dimension can be hydrogen, nitrogen, carbon, anything. Suppose if you have three dimensions, you have hydrogen in one dimension, in the second dimension you can have nitrogen, third dimension you can have carbon. So simultaneously you can detect all the nucleus at the same time. So that is why people use the multi-dimensional experiments for this one. So again, the same thing. That's why I told you go from a sensitive nucleus to the insensitive nucleus for this one. So this is how you take a peptide bond and you look for it. You see, if you take a peptide bond, you have a NH, you have CO, NH is the peptide bond. So between two amino acids, every amino acid you have a N-terminal NH. So that is what you are going to detect first. Suppose if I take a peptide or something, now you see every amino acid belongs to a peak. Y-axis is nitrogen, x-axis is hydrogen. This is something like this. You will see a protein like this. Every dot represents an amino acid here. The number of amino acids in a protein is very much equivalent to the number of amino acids, number of dots which are present. You see, if you do a one-dimensional NMR spectroscopy, you will not know whether a ligand is binding to the protein or not binding to the protein. You will not make it. But when you do a two-dimensional NMR spectroscopy, you see the ligand is binding, but it is not binding to G33, G48. It is binding to K22 or G70 or something. Not only you can tell where it is binding, how it is binding, where it is binding also, you will able to tell. So similarly, this is one example. If you have this one, you will never know what this protein is. But if you record a two-dimensional NMR spectra here, actually this is only 70 amino acid protein. 70 amino acid protein should have only 70 dots. But roughly, I am telling, if you count these dots, you will get around 140 dots. Why 140 dots here is, how can 70 amino acids will give 140 dots? Essentially, this molecule is in a equilibrium of monomers and dimers. So now, you see, for every dimer peak, I can show you a monomer peak also. So this is monomer, this is dimer. So again here there are two peaks, monomer, dimer, and so on. So forth. You see, the monomer, dimer of dimer, monomer, dimer, monomer. So dimer monomer. So you can not only, that is what I am telling, you can see various conformations also. That is what in the nano I showed you, even with Wurtzite conformation and everything, you can see different conformations, and you can see this for biomolecules which are tough. Not only that one, you can use and you can see whether a protein is folded, partially folded or unfolded. So if a protein is folded, you will see in such a way that the protein peaks here are very well nicely spreaded and dispersed. The reason being, in a folded protein, your three-dimensional structure, you have a very unique three-dimensional structure. So every amino acid have its own environment, microenvironment. That is why you will see a nice folded thing. But whereas partially folded, you see, the portion which is unfolded, you will be clumping. The remaining portion, it will be nicely dispersed. Whereas if it is completely unfolded, everything will be clumping. So you can see, you can do a simple experiment of NMR and you can tell whether you have a folded, partially folded or a completely unfolded structure. So now with these, what you can do is you can solve the problem of protein structure folding and everything. You see, this is how in the picture a protein is going to fold from an unfolded to a folded structure. So what we can do is essentially we can, as I told you, we can solve the structure of a protein using NMR spectroscopy. So how do you solve this structure? So what you will do is you will measure the coupling constant, you will measure the chemical shifts, you will measure the nuclear over-Hauser effect space correlation, and you will add them into a software, molecular dynamics software, where you can generate restricted molecular dynamics, where you can generate the things. So first you assign the amino acids, which are these amino acids, and you see from distances which amino acid is how far from what it is, and then you calculate the structure of this one. So which is, I will show you here. So you take a protein, you label the protein, you collect the data, you calculate. We know protein, right? We have primary structure, secondary structure, tertiary structure, and everything. Of course, whether you get a quaternary structure or not, if I am talking about the tertiary structure of a protein, that means the structure of a protein, I should get a tertiary structure. Okay. So first I will get the secondary structures, then I will get the tertiary structures. First, you will analyze what are the secondary preferences. So what is a alpha and what is a beta preference. So these are alpha preferences, these are beta preferences. So you have to know like alpha beta. How do you know alpha beta? So you will put the NMR restraints in a Ramachandran map. So when you put it in a Ramachandran map, you will know this is a beta region and this is a alpha region. You will know which amino acid is behaving like alpha and beta. So similarly, you can also tell the alpha helix and beta sheet by using something called a Karplus equation. Okay, so this is what the coupling constants are. For a coupling constant, the beta sheets will have 8 to 10 Hertz and alpha helix have 3 to 4 Hertz. So you put all these things, then you can also do something called hydrogen exchange. So the hydrogens which are present with the nitrogens with carbon, essentially they are hydrogen bonded in a structural element. If you see this hydrogen, this is present in a structure. If you don't see it, it is not. You see, all these hydrogens in a beta sheets are essentially hydrogen bonded. So that means you will see. But at the same time, this hydrogen, this hydrogen, this hydrogen, you won't see when you add D2O, they will be disappearing. That is what happens. This is HSQC, but when you add deuterium, you will see only few of them which are coming here. So this will tell these are the hydrogens which are present in the structural elements of a given protein. Now, once you get the hydrogen bond constraints, once you get the resonance assignments, all alpha helices, beta sheets, and everything, then the main thing comes into picture. Now you see the solid line, and for every line there are dotted lines. That means if I take a protein from here to here, the protein may be around 30 Armstrong or something. Okay, similarly, like from top to bottom, 30 to 50 Armstrongs. Now, how can I calculate the structure of 50 Armstrong if I can only measure 5 Armstrong units in the distance? So then what I do is I measure from here 5, 5, 5, 5, 5. From here 5, 5, 5, 5, 5. Like that, the whole protein. That is why you are seeing a network of interactions. What you do is every point you make it as a nodal point. Each node you are trying to get the information. This is what you do. So you put the restraints and you go on going through a iterative cycle of structure. You see, initially you have less restraints, you have a worse structure. Now you add more distance restraints, you get a better structure. You now add much better, then essentially you see a very nice structure. That is why by using NMR spectroscopy, when you do a protein structure refinement, you always, in the protein data bank, you always put something called 5 structures or 10 structures. You call it as an ensemble of structures. So all these structures should come. Now, to be frank, you don't have to worry too much. You have automatized softwares for these protein structures. So you can give all the NMR spectrum and everything. They will try to do the hydrogen bond distances, the dihedral constants, and so on and so forth. And finally, they produce a nice structure like this. As I told you, the more the NMR restraints you put, the better the structure you are going to get. Now, suppose think of you got this structure. How do you know whether this is correct or wrong? So if you get a structure, you have to tell this is correct or wrong. To go to correct or wrong, again what you do is you go back to something, the Ramachandran map. So all the constraints, whatever you put, has to follow the Ramachandran allowed regions or generously allowed regions. So if your residues are not falling or your constraints are not falling, that means you have done something wrong. And the best way is you go back and essentially redo the analysis, then correct the structures. So then once you do this one, you can identify any regions where the ligand binds or something, and also, as I told you, NMR can be used of, we can discuss this in more. You can do lot of dynamics here. And how do you do this thing? You have something called in NMR order parameter. Order parameter will go from 0 to 1. Order parameters goes from 0 to 1. 0 means flexible, no order. 1 means very order. So if you take a protein, you see these are structural elements. Okay, these are the structural elements. Wherever there is a structural elements, there is a order. Okay, and wherever there are no structural elements, okay, ending, there is less order. You can compare with the RMSD of crystal structures also, and you can tell where you have order and where you don't have the very flexible and rigid. So if S square is 0.8, 0.9, that means these portions are rigid and these are flexible. You can see this cartoon. The larger the loop, that means it is flexible. The sharper it is rigid. Okay. So I will show you now few examples that we are working how to engineer a protein or how to see the protein ligand interactions or something, so that you will understand more about the practical applications of the NMR spectroscopy. So this is one thing, uh, you know, as I told you, I showed like you can see the oligomerization, monomers, dimers in this, but the same thing, you see, here you have 140, here you have only 70. So that means this protein stays in one conformation, whereas this protein stays in two conformations. Using NMR, you can essentially assign all the conformation. You see, every amino acid present in the protein, I am assigning. These are all my conformations which are present. So I can tell which conformation belongs to which and which amino acid, whether it is a monomer, dimer, or something. What I did is, we did is, we took this monomer dimer, and what we did is, we added a disulfide bond between the two monomers. When you added the disulfide bond between two monomers, what happens? So now this remain as a dimer. Now it cannot go between monomer and dimer. So now you will see only one set of peaks instead of two sets of peaks. So that also you can identify. Now you take a ligand and you add it to the ligand. Now you see, when you add a ligand, here a small carbohydrate octasaccharide is added. So when you add it, this is the residue numbers. You see, here it is binding, here it is binding, here it is binding. When you put on the structure, the red patch is the where actually it is binding. This is not binding on this surface, it is binding on this surface. If you calculate the structures, so this is how it looks like you have the protein and the carbohydrate is nicely sitting on the top of this one. Now, when we analyzed, we found that there are 4 amino acids, K62, K66, K22 and histone. So it's the electrostatic surface, positive surface is binding with this ligand, since all these yellow and red dots are sulfate groups. So the negative and the positive charge are interacting with each other. Okay. So now, how do we know these are exactly interacting? What you can do is, you can basically do a mutagenesis. You convert everything into alanine, then I will show you. So you convert everything into a alanine. So what happens? You see this one, nicely shifting peaks, everything which indicates binding. Now you see, nothing is shifting, everything is at their own place. That means now the protein cannot bind to its ligand. So that means these are the 4 amino acids which are essentially the reason for binding. You can also tell, now I said whether it is binding on these 2 helices. You can see the 2 helices it is binding. Now this is the helix. Okay. So before binding, you see the blue dots, it is all over the place. That means they are flexible. But once bind to the helix, you see all are in a straight line. So that means it is stabilizing the helix. You can also see the stability of the helix. You see, these are all the helix residues. In the hydrogen exchange, when there is no ligand, they disappeared. But when you put the ligand, all of them are coming into the spectra, indicating that they are essentially, it is binding to the helix. Not only you can tell they are binding to the helix, what you can do is, you can actually measure the, as I told you, you can measure the thermodynamics and of the protein. So how much actually the delta G gained by binding to this one. You see, the whole helix has gained almost 4 to 6 kilocalorie of delta G upon binding to its ligand. So you can map the surface, you can understand the surface, you can bind to the surface, and you can also get the thermodynamics, kinetics, and so on, so forth of the information. So you can add a ligand and you see there are 2 peaks Now, when you add this ligand, it is going to one peak. What it indicates is essentially ligand-induced dimerization. So the ligand actually is binding here and it is inducing a dimerization which is forming the dimer part of it. So you can check how these dimers forms, and you can make homodimers, heterodimers, so on and so forth, and essentially you can talk about the how the mechanisms happen inside a biology by using a comprehensive studies of these NMR based ligand interactions and so on and so forth. Okay, so I will give you one more example for another 10-15 minutes or something. This is again different class of protein where you can engineer proteins also here. Not only you can study proteins, but you can also engineer proteins for it. Okay, so this is one another class of protein uh, which are called the bacteriophages. So bacteriophages have some proteins called endolysins. Okay, so these endolysins are essentially considered as next generation antibiotics or antibiotics. The reason being they can kill the bacteria. So now there are various endolysins and everything. Now I will show you one of the endolysin, which is the T7 bacteriophage endolysin. If you see this T7 bacteriophage endolysin, you see again some of the residues, it's not all the residues have doubled, but some of the residues have doubled. L108, 108 frame, 101, 103. So that means this is something which we call the conformational heterogeneity. If I see this as a N terminal of the protein and this as a C terminal of the protein, you see the C terminal of the protein is essentially heterogeneous in nature. That means you are seeing different peaks here, whereas not in the N terminal. So now, protein dynamics is something which is very essential for the protein to have activity. Now the question is, can we actually identify why this heterogeneity is coming and from where it is coming, what is the source, and can we quench the heterogeneity or something or reduce the heterogeneity so that we can engineer a better protein out of this one. So we have done this one. So essentially when you go to a lower pH, what happens at pH 7 it is folded. Now you see at pH 5 or 4 they becomes partially folded and loses its activity. Only at 7 and 8 they have activity, 6 they have 50% of activity, and lower pH they lose activity. The reason why they lose activity is essentially a lot of studies we have done, and we have seen that there are 4 histidines which are present in this protein, which forms a network of these histidines. Now what happens is these histidine networks essentially they protonate. When histidines protonate each other, then there is a repulsive interactions now which made the protein from when you go to 7 to 3 it forms a partially collapsed form. Now the question is, if histidines are the real reason, when you go back from pH 3 to 7, then they should deprotonate and they should give the same spectrum. Of course, you see at pH 7 and when it goes to the reverse pH, essentially they come back. So that means it's the protonation and deprotonation of these residues which are essentially generating such a chaos. So now what we decided is, so we decided one of these histidine which is present so that we can play with it around and we can engineer an enzyme. So what we did is we didn't touch the binding site and we have taken one histidine which is little away from the binding site. Okay, this one. So what we did is we generated the mutants. If you see this one, if you knock out the histidine at that place, you have almost 30 to 40% increase of the activity which is present in this. Now How the activity is increased is when you remove this one, what actually happens is, as I told you, we have some minor conformation and a major conformation. The major conformation is essentially strengthened, whereas the minor conformation is weakened. And also, if you see, all these red dots are essentially very dynamic in the wild type, whereas in your engineered protein, you see, all of them are almost very similar. That means since you knocked the histidine, which is creating these dynamics here, these dynamics are lost, and essentially the catalytic site became very rigid. This catalytic site became rigid, that is why you are seeing the enhanced catalytic efficiency or the enhancement in the activity of a given protein. So now, of course, we studied, you see, this is the catalytic site, what we know. The proteins we also studied in our basic biochemistry textbook and everything, that proteins can have very long range, uh, you know, interactions. So this is around more than 20 Armstrong units. So they show long Armstrong units. If you see, this is the helix we are talking about. If you remember, this is the one which we are talking about, where we have heterogeneity. So that helix is now essentially perturbed, is controlling by this helix in a very long range interactions, and that is how essentially you generated an enzyme with high activity. So in order to accommodate a high activity enzyme, what it needed is it enhanced its activity, it restricted its dynamics, altered the heterogeneity, that means conformational population it altered, and it actually reduced a little bit of stability here. So that is why we call it as essentially a stability activity trade-off. That means it has to forgo a little bit of activity in order to enhance uh, its activity. It has to give a little bit of its stability so that it can behave like a better enzyme of its own. So these are some of those conclusions, like sort of, protein plasticity is actually, proteins are evolutionarily plastic. So we can use these conformational dynamics to engineer the proteins, and such structural and computational biology offers these proteins for their recognition, ligand inhibition, recognition events, so that we can generate next generation therapeutics, and we can also understand the molecular mechanisms of these many pathological and physiological uh, functions. Okay, with this, I will stop. So this is our group. A lot of people have graduated and contributed to this work. Several of the collaborators, funding, and so forth. And with this, I thank you all for your kind attention. I will be happy to take whatever the questions from your side.
Thank you, sir.
Hello.
Yes.
Uh, yeah. Dr. Krishna, am I audible?
Yes, yes, Chandan. How are you?
Yeah, I'm fine. How are you?
I'm good. I'm good.
Yeah, so thanks for wonderful lecture. Uh, my question is basic. What's the biggest challenge when someone is working on proteins and someone is trying to study proteins using advanced spectroscopy?
See, the few bottlenecks are first, unlike your crystallography or cryo-EM, you need to have recombinant system. So you have to, it's like, crystallography and cryo-EM, they can take a natural proteins and they can still crystallize it.
Yes.
But for NMR, you need to produce a recombinant protein, since then only you will able to label with 13C and 15N. So production cost of these proteins uh, is, and make it being folded in the conformation in especially E. coli. If you go to mammalian expression systems, that will be costly. So as long as you can able to do this one, so then protein interactions and structure, now up to almost 50 to 100 kilodalton you can do by solution state NMR very comfortably.
Thank you. Thank you.
Okay, thank you.
Any question from the audience participants? Please, you can ask, sir. Dr. Namrata Rai, madam.
Yeah, I am seeing the question. Yeah.
Okay, sir.
Yeah, ma'am, actually you can study protein aggregation behavior also using the NMR spectroscopy. People have studied protein aggregation, especially amyloid beta fibrils and synuclein. So these proteins you can study intrinsically disordered proteins also, IDPs. So you can study the aggregation behavior, how the seeding happens and everything. You can essentially do the NMR spectra, like along with time you can also study the kinetics of aggregation. But some of these structures, when you do study with the NMR and everything, so finally you would like to take the transmission electron microscopy or something for the images, so that the final forms will be the aggregated state. So people even have confirmed and compared the THT fluorescence studies and everything, thioflavin T, with the NMR kinetics and everything. The best thing with NMR is actually you can study the kinetics of each and every amino acid present. THT will have only one curve of kinetics. You see, lot of things what we do in NMR, you can do with CD, fluorescence, or ITC or something. But they give only a globular picture or global picture of it. It gives only one parameter. But whereas, like suppose you do a CD, you say like helix is unwinding. You don't know where exactly it is unwinding. Only you know from 40% of helix it goes to 25%. But with NMR, what you can tell is exactly which 4 amino acids of a helix is unwound, or which are actually, you know, engaging in a oligomerization or dimerization and so on and so forth.
Okay, thank you, sir. So I have studied protein aggregation using very basic methods like optical density measurement and through DLS measurement, but not through any spectroscopic angle. So this was very interesting to know. Thank you,
Yeah,
sir.
sure. Yeah. Thank you.
Any other questions from the audience, please? Any other question from the audience, please?
Okay.
Or participants can raise their hand or write in the chat their questions. Is there any other question?
If there are no other questions, then we can conclude this session right here. And we once again thank you, Professor Krishna Poluri. Thank you for your nice presentation.
Yeah. Thank you very much. Thank you all. All the very best. Thank you.
So now we are going for a lunch session, our lunch session, which is from 1:30 to 2 p.m. So we will again meet at 1:50, I think. Thank you very much.
No, am I audible?
Yes,
Yes,
ma'am.
yes,
Yes.
ma'am.
Okay, 1 second before the participants leave. Uh, is Mr. M.R. Ramesh in the session? And Mr. Vignesh, are you in the session? Kindly respond. Mr. M.R. Ramesh. Okay, we will conclude the morning session now and go for the lunch session. And we will meet again at 1:50 p.m. Thank you.